Hello, everybody. Are you guys listening to me? Cool. Wait. Yeah. So, thank you, everybody, for sticking around for our last talk of today. And my name is Eugenio. I am currently a master's degree student at USP. I'm currently working with anomaly detection, which is a completely unrelated topic to this talk, but I did it for fun, this talk. So I will explain to you the whole process, the whole idea, the step-by-step, without going too much, without giving too much detail on how I did it. If you want to discuss afterwards about this project, fine, you can chat with me, we can spend hours on it. And yeah, there is a lot of simplifications of this problem. I haven't seen anyone talking on this, so it might be some very serious simplifications. But at the end, you see the final result of the model. Okay, the idea here, just to remind you, is that I'm not going to pretend to be a comedian here. I'm just give the algorithm to learn how to detect laughs. That's the whole idea. So, the goal of stand-up comedy is to make people laugh, right? So this is a very challenging profession to follow because there is a lot of sensitive aspects in this area. So some people think it is a form of expression, a way to express their ideas, or in other words, it's art, but others see it as a business. So as a business, you want to maximize your profits. And to do this in this business, you need to deliver laugh as much as you can as a comedian. So there is a rule of thumb that most comedians follow. Actually, it's just a guideline to follow. So that's the sentence. A comedian should deliver 4 to 6 punchlines every minute that they are on stage. Think about it for a second. This means that every 10 to 15 seconds, the comedian should deliver a joke or a punchline. For 1 minute, this is really hard. And for 1 hour, well, it's way harder. And I was wondering to know if that is true. I went to analyze one video, for instance, and see if the comedian is delivering this much of punchline. So that's what I went to use. I went to use a machine learning algorithm to detect the laughs of the audience, and then we perform some analysis to see if the comedian is following this rule. So I will pretend that you guys don't know how a stand-up comedy works, and I will give some conceptualized version of it. So, okay, I will call them agents. We have 2 agents in a stand-up comedy show. The first one is the comedian, and the second one is the audience. These are 2 agents. They interact with each other, to each other. They have a set of different actions. For example, the comedian he is talking to the audience, and he can also laugh or make sounds, like opening the door or something like that. And the audience usually can clap or laugh or reply to some answer that your comedian is doing. And that's the basic idea. That's the basic dynamic. Because and there is another important aspect, because when the comedian is talking, the audience is in silence. And when the audience is interacting or acting, the comedian is in silence. Of course, this is an oversimplification of the problem, but we will assume this here. Another aspect is the video recording. most comedians record their videos and publish online, and which makes very good for us to download this video and perform some analysis. And yeah, but how can we detect loss, right? I will give the intuition here. I'm not going into too much details. I'm not going to explain the codes and everything behind it. But there is, at the end of this talk, I will give my GitHub account so you can check the repository in there. So let's imagine this stream of audio, right? As a developer, you can think as an array of floats, right? No more than that. What I want to see at the end of my algorithm is this. These green bars are essentially the segments, the moments that the audience is laughing. That's it. I want to find these segments. I want to define these segments by the algorithm. I want the algorithm to learn this pattern, right? So let's start. I will explain the whole pipeline that I did to develop this project. So here we have the data collection problem, the data collection step, sorry. And I will go back to this slide just to make sure that you are following the step by step. So for data collection, we have essentially 3 steps. The first one is to decide which comedian we are going to analyze. Of course, there are so many comedians out there. Some of them are at their beginning, and some of them are some of them are very expert on this. And I decided to go with the most popular one, which is named Thiago Ventura. I'm sure you all know some of it, know him. And of course, we need to choose a platform to download the videos, the content that we can analyze. So I, of course, select YouTube to do it. And then I picked a handful of videos. In this case, I did with around 15 videos. And the data labeling, I will explain later, I did with, I think it was 2 videos, about 6 minutes each. So that's the idea. And also, I downloaded the metadata of these videos, which means that this is information that is not available in the video itself. For example, is the number of views, the number of likes that this video got. This is important for us. So I will explain why later. So to download the video, I used this library named YouTube DL. If you don't know, it's a very good one. So you can download the video. You just need to pass a list of URLs of YouTube or other platforms as well. They can support, I guess, Vimeo or something. And the options. For example, the option is the video quality, the audio quality, and some other more detailed aspects of it. And I also specified here in these options to extract the audio stream of the video. I'm not performing any analysis on the video. I'm only using the audio, right? So that's why I'm specified here in these options. In this slide, I'm not showing the options here, but the source code you can check it. So we download the video and we extract the information. The information is our metadata, right? So here I just want to remind you that I'm not using any video. I'm just doing with the audio, right? So from the video file, I'm extracting the audio stream, right? Cool. We have our data. I already have downloaded them. I have the file format that I want, and I need to label it. Why should I label my data? Well, the labeling process is I need to teach my algorithm. I need to give some label to say, hey, algorithm, this is a laugh, or this is a talk, or this is a yados, or whatever. This is clapping. I need to label these segments, right? Otherwise, the algorithm won't be able to decide what is the pattern that he is seeing. So let's go back to our original image of our two agents. For the first one, the comedian, I will oversimplify here, right? But the comedian can do like 3 actions in this case, like then talk, laugh for his, I don't know, for his own jokes, who knows? But he can interact with the audience and that kind of stuff. Of course, this can go beyond this. Like he can make sounds, you know. There is a lot of other events that you can track. But here we are only considering this. And for the audience can clap, can laugh, and of course can interact with the comedian at some point, like replying some Q&A answer, you know. And of course, we need to specify as well the hiatus. The hiatus is important here because when the audience does like a very low laugh, the algorithm can get confused. So we need to explain this pattern to the algorithm as well, right? So one library that I used to help me with this is Audacity. I'm sure that you guys know this library. If you don't know, it is a audio editor library program that you can download and use it. So I got my audio stream and put inside of this program. That's the first image that you can see, right? This sound a bit scary, but it's not. At the top here, we have our audio stream, right? And at the bottom, we have the label track. This label track we can add at Audacity, and then we can manually label these segments, right? This is a very time-consuming task. That's why I did only in 2 videos. These 2 videos has about 5 to 6 minutes, but I segmented the whole audio stream. So, for example, this first part here, I got the talking. I segmented the talking. This is a very low variation in the audio, as you can see. There is a little bit of noise. But when we see the clapping, it's very louder. There is more spikes here. This is really good because we can teach our algorithm with more easiness that these 2 patterns are different. Of course, our interest here is laugh and clapping, but you got the idea. These patterns are important. And once we get these labeled, I can teach the algorithm more easily. So at the end of my labeling step, I did this whole segment. Each segment has a label. For example, the label T stands for talking. The label C stands for clapping. The capital H stands for hiatus, and so on and so forth. Right? So that's the basic idea. We can save this file, this label, into XML-like file, so we can read later for us to specify the label of each segment. Cool. This step is the most crucial one for our model. Of course, the previous ones are also very important, but this one is very important to teach the model what we want. So how we did it? What is the feature engineering here? What I want to extract from which features I want to extract from this stream of audio? There are a handful of them. I'll explain them later. But the idea is the following. I cannot use the whole audio stream and fit into my algorithm because the algorithm will not easily learn that. We need to find something different to do it. So the idea here is to crop each in different segments of 1 second segment. This 1 second segment, it's what I want to do for the whole data set. And I will shift this data set in 100 milliseconds. this is in other words, you can see as a sliding window of 1 second with 100 milliseconds per shift. And I do this for the whole data set. So we break down into smaller pieces. And at the end, I have information for each segment. I can filter actually by the segment, the label of the segment, and then create into my model, right? So I'm not sure if you're familiar with audio files, but in 1 second of audio, you can think of kind of as a 48,000 vector of float values. This is huge because for our model, the algorithm doesn't learn that quite easy. So we need to perform, we need to extract relevant information from this whole stream of segment, right? So, okay, at this point, what we have the segments and the label for each segment. What it means, like this segment has some laughing, has talking, and that kind of stuff. And each segment represents an instance, or it represents a row in my data set, right? And the columns here, for now, it represents a 50K float vector. But this is not good. So what I'm going to do is to extract important features from this. There's a really good library that we can use. It's named Librosa, which is audio and music analysis library. In their documentation, they have a set of functions that you can use to extract features. And I could use all of it, but picking only these, I think it was 7 or so, it was enough for my model. So the idea here is for each function, the function returns array of elements as well. So I got the average and the standard deviation for each one of these features. At the end, I ended up with 31 features. Some of these features can produce more than one other feature. So that's our model, like 31 features, spectral features actually, and that's it. And for each instance, represents a segment of your audio. Cool. Just wrapping up, the idea here then is get the first second of it, and of course we have the label of it, of this 1 second, this 1 second segment, and we apply the same segment in every feature for every one of these functions that I have mentioned before. So that's it. I got my 31 features and a set of instances. Cool. The modeling part. At this point, we have the data set done, like a set of instances and 31 features. And our 3 classes. In other words, I'm transforming this into a multi-class problem. If you don't know what it is I have 3 classes, like talk, laugh and clap, and IATAs. I just want to teach my algorithm these 3 patterns, right? And we are done. We are done for now, but we need to decide which classifier or which algorithm to model. And the algorithm that I picked was a multi-layer perceptron classifier. Actually, it could be anything else, like you could use a deep learning or something, or you could use a random forest or any other algorithm. But this one was okay, and ended up with a good result. And the input layer are 31 features and 900 neurons, and the output layer is only 3 classes. And I only used one hidden layer, which makes a quite simple model. And the output of it, this algorithm, is the following. For each segment, we have the label, right? So to reconstruct this in a way that I can see if there is some laugh or not, just want to consider when there is no overlapping between these segments. I only consider, for example, the love part. I only consider the last part of it because there is no overlapping with the talking. In other words, I just want to make sure that my algorithm knows when exactly only laughing is happening, for example. Cool. The visualization step. I can do this in 3 different ways. The first one, I can export the results into a subtitle file. Just like if you have watched Seinfeld or Big Bang Theory, you might have seen like the subtitle remind you that a joke is happening, you know. So this is one way to do it. Another way is vertical bars, just like I did in the beginning. Each of these bars represent the moment that it started, the laugh is started, and when it's ended. And the thickness of these bars represent the duration. But in this model, I'm not considering the duration. Of course, this is important, but I'm only using I'm just interested on counting these moments. Of course, this might lead to some errors or something, but that will solve our problem for now. And the last one is the temporal. We can see how many laughs per minute the comedian is delivering over time. So this will be useful to answer our question, our original question, which is we want to know if the comedian is delivering 4 to 6 punchlines every minute. So the temporal one is a good option. Okay, I will show you the video. I hope you can listen. But the idea here is that you can see the synchronization of the output of our subtitles with the audience laugh, right? This is not the perfect model. We can fine-tune this, but the idea is to see that the simple model, the output of this simple model. Okay, so I hope you can listen to this. Oh, cool. Okay. This is just a very small example.
Please see. Let's salve, save. É nada, és nothing. Moleque piranha, fish boy. A gente vai no fluxo. Aí eu falei assim, what's the figure? Se você não é de quebrada, você não entendeu o que eu disse.
Cool. Okay. The idea here is to show you to show you that the algorithm is able to detect the beginning and the end. Of course, there is some delay, as you may have noticed, I hope. And we could do this better. For example, we could use we can resize the size of the window. For example, if I want to use the 2-second or 500 millisecond of the window, I could use that, and that would imply directly on the output of this model. Of course, the shift of each time window is important to notice because it differs on. It will imply on the overlapping of each segment. And yeah, that's the main idea of the strategy. But of course, we can, as I just mentioned, you can tweak to get a better result. One way to see if my algorithm is performing really well is visually. Okay, just like I showed you, you can see visually if it is a good video. But another way is to rely on views per like. This is not a perfect metric. It could be better, but for our purpose, it was okay. What is the idea here? If the video has one view and one like, is a really good one. If this ratio is close to one, cool. The video is really good. And the larger this number goes, the worse the video tends to be. But this is not true for all cases, because the intuition here is that the number of views grows faster than the number of likes, which which means that older videos may have the disadvantage. But since I just picked very recent videos, it was okay. So let's see an example of a popular video, right? What I mean by popular here is based on these views per like, which means it's a very low value. And see what is the output of our model. Let's see if it makes some sense. So here we have, let me see, okay. We have the example of popular video. The first chart is the number of laughs per minute over time. And the red bar, the red line, represents the threshold of 4 punchlines per minute. And at the bottom, we have the barcodes, this barcode chart, which means that the moments of each laugh. By these two charts, we can see that the video has more laughs and at the beginning, right? And not too much. Oh, I'm sorry. This video, you can see that the number of laughs is well distributed across the show and not very concentrated in specific parts. And most of it, the algorithm says the same thing, which is the output below. And the number of the views per like, which you can see at the top, is 12, which means that every 12 views, we got 1 like. So this is a popular video based on my small data set of videos. So the algorithm seems to indicate, to suggest that the rule of thumb is true for a good presentation, right? So, but we need to see an unpopular video as well just to contrast. Just a quick reminder: this output that I'm showing is from the same artist, right? Just keep that in mind. And this is an unpopular one, and we can clearly see that at the beginning of the show, the comedian is outperforming the 4 punchlines threshold, and after the beginning, he cannot keep up with the same delivery rate of punchlines, and we can clearly see this on our algorithm. And of course, what I mean by unpopular is we can see at the top, which is the views per like, that is 30, which is more than double than the popular one. And the algorithm was able to grasp this information just by learning and detecting the loss, right? So, the conclusion. These preliminary results, of course, I just showed you 2 very small examples of this, and these indicate that a good comedian or a good show delivers 4 to 6 punchlines every minute that they are on stage. Of course, I'm not strongly stating that this is true for all cases, because I would need more data to analyze. I would to be very rigorous on this. So I'm being very cautious with this. But yeah, for this project that I did for fun, without much rigor or without much thinking, we can see that there are some good results with that. And the idea as well is that you can extend this for other applications. For example, here we are only using we can use as a comedian coach, if you want to say, like if you say the comedian is performing very well or not. And we can use this same tool, the same algorithm, the same strategy. For example, video editing. The editor wants to know which moments to place some joke or something like that. So based on these charts and based on this information, the editor can do it. Of course, we can do it in real time, or at least near real time, by doing the performance of the artist. We can track the laughs and the duration of it. Of course, we can also detect the intensity of the laugh and the duration. Here I'm just counting the laughs. I'm not considering the duration. This is very tricky and might have led you to some different conclusions. But yeah, that's the other aspect of this problem that we can explore. So, thank you guys. If you want to chat about this, you can approach me. I did a post on Medium explaining a little about of this algorithm, this project on Medium. It explained better in more details than here. If you want more details, you can go to my GitHub account. There is a stand-up repository in there that you can check the code. I separated by data collection, feature engineering, modeling, so we can visualize all these steps independently. And yeah, you can add me on LinkedIn or you can talk to me by email. So that's it. Thanks for all, guys.